Hi everyone, welcome back. So today we'll continue on our lecture series on applied electromagnetic theory. And today we're going to do something. This is lecture 24, if I'm not wrong. Maybe I'll just erase that. Today we're going to discuss fiber optic cables. Okay, so fiber optic cables are nothing but circular dielectric waveguides. So since we have been dealing with cylindrical waveguides, it's a good time to talk about fiber optics. So if you're dielectric waveguides, and specifically, we will discuss what is called the step index fiber optic cable. Okay, so in the world of waveguides, fiber optics is really the king. It's the most widely used, one of the most amazing technologies of the 20th century. It makes the high-speed internet possible, and it's really an amazing technology. And so hopefully you know about fiber optics and the importance of fiber optics. Okay, so that's what we want to discuss today, and we want to do a slightly more rigorous kind of discussion than what is often found in some of the books, right? So this is a combination of material that I pulled from different books. Okay, so let's get started. So what does a fiber optic cable actually look like? It has a cladding, right? So it's kind of a large cladding, and inside there is a core. It's not a very good core. Try that again. Okay. So this is core, and then you have a cladding layer. And typically beyond the cladding, there is also a jacket. So let me actually draw that. Well, so this thing is kind of a protective jacket that's usually used. Okay. So I'll call this the jacket. And then this is your cable. The actual cable is kind of, this is just the cross section. Okay, so we'll label the core as n subscript d. That's the refractive index, which is square root of epsilon d mu d. And the cladding layer is square root of epsilon c mu c. So the way I've drawn it here is not to scale. Typically the core is very small and the cladding is very large because you want the fields to decay completely before you reach the jacket. But I've not drawn it to scale. So we'll call this region 2 and we'll call this region 1. Okay, so this is the cross section. And typically the operating wavelength, so when you're in optics, you deal with wavelengths more than frequencies, is usually 1550 nanometers because the loss is the lowest. It is only about 0.2 dB per kilometer. So this is one of the reasons that this 1550 nanometer band is very popular for long range fiber optics. Right? Another band that's popular is the 1310 nanometer. So this has the lowest dispersion over wide bandwidth, so over a large number of frequencies. So this is also a popular band for short range cables like Ethernet and so on, or data centers, right? Where you're putting a large amount of data over short ranges. Okay. Typically, ND for the core is approximately 1.45. That's the dielectric, that's the refractive index. And the material is some kind of doped silicon dioxide. Right? Dope, sometimes also called silica, which is nothing but silicon dioxide. And the cladding, which is NC, is approximately 1.44, and this is pure silica. So they're very close in their refractive indices, and that actually is quite significant. We'll see what the importance of that is later. Okay, what the importance of making them almost equal. Okay, so what we want to do is we want to solve the wave equation, see what kind of modes exist, what kind of modes are desirable, what is their propagation constant beta along the z-axis, the mode profile, and so on and so forth, right? So that's what we want to solve, and that's what we're going to do now. Okay, so I have a wave number a rho along the rho direction, and I know it satisfies this equation from our previous video where we showed that for cylindrical waveguides you have a dispersion relation which relates, basically k rho square plus beta square is k d square. This is inside the core, which is nothing but omega square mu d epsilon d, which is what k d square is, minus beta square. And then inside the cladding, which is region 2, the dispersion relation is AC square minus beta square. And beta is the same for both from phase matching, right, which we saw last time. This would be omega square mu c epsilon c minus beta square. And we want to say that this is equal to minus nu square for some nu. And the reason we do this is because we want in the cladding the waves to be evanescent, which means k rho must be imaginary, right? So basically I'm saying k rho 2 is equal to I nu. And nu here is real. Let's say nu is a real number. Okay. Okay, so since we kind of established that in the cladding you want an evanescent wave, and in the core you want a propagating wave along rho at least. So essentially rho should be like some kind of a standing mode inside region 1, and inside region 2 you want an evanescent or decaying mode. Right? So we know basically from our last lecture that if it's a standing wave in rho, then that takes the form of the Bessel function Jn k rho 1 rho, and the phi dependence is just e to the in phi. Right? The reason we use the Bessel function of the first kind is because we have the origin, which is the center. Let's say the coordinate system is like this. Since the origin is part of the domain, we can't use the Bessel functions of the second kind because they have a singularity. Right? So since we don't have a singularity, we end up with only the first kind. And in region 2, we want the modified Bessel functions, which are exponential decaying functions, right? Instead, we can also write it as the cylindrical Hankel function, hn1 k rho 2 rho e to the in phi. So this is in cladding, right? And this is nothing but equal to 2 over pi I to the n plus 1 kn rho nu, right? Since k rho 2 is equal to I nu. So basically you take k rho 2, you substitute I nu in here, then you use one of the relationships we developed in the last lecture, which relates the Hankel function of the first kind with the modified Bessel function of the second kind. Right? And these are decaying exponentials. We saw that. They're very similar to decaying exponentials, right? And that's what we want in the cladding region. Okay, so I should say that this is the modified Bessel function of the second kind. Okay, so these are essentially the values of, or the kind of psi that we're looking for. So we're looking for solutions of this kind, right? So what does this actually look like? So if you actually draw it out inside the core and cladding, so I say that's my cladding, and I have my core here. Then these functions look like this. So it's something like that, and then it decays exponentially in there. So that's one mode. Another mode might be something like this. Maybe I should redraw that. Okay, so let me actually just make a line here. Okay, so mode profile may be like this. Right, so it's a kind of sinusoidal in the middle and then exponentially decaying. Or it could have mode profile like this. or it could have any of the other kind of higher order modes, right? So maybe I'll draw one more. Maybe it's like this. And so on. Right. So these are just kind of distributions that I've drawn for the psi values. This is not the electromagnetic fields, right? That is somewhat more complicated. But what I've drawn right now is that. So basically in this region, we have the Jn, and in this region and this region, we have K sub n, right? Okay. So let's go ahead and find what the fields actually look like. So fields. So once we have psi1 and psi2, what we need to do is find the fields and apply the boundary conditions, right? To find what the coefficients of these field quantities would be. But interestingly enough, when you have a dielectric waveguide like this, or a fiber optic cable like this, the TE or TM modes alone don't satisfy with the boundary conditions. So I would say in general, we'll see in which case you get TE and TM. But in general, TE and TM alone cannot satisfy boundary conditions. So we need a combination of TE and TM modes, which are called hybrid modes. Okay, so let's actually see how they show up. So what we'll do is we put these kind of potential functions into the equations to find the fields, which we discussed the last time. Right? Once we have the cross-section potentials, from that we can get the fields, right? So in region 1, what do the fields look like? So here I'm just writing the z component of the fields. So EZ1, be K rho I, K rho 1 square, AN, JN, K rho 1 rho, E to the I n phi, E to the I beta z, and HZI, or I should say HZ1, because region 1, be K rho 1 square, BN, JN, K rho 1 rho, E to the I n phi, E to the I beta z. Okay, so you can kind of see that have EZ and HZ component in general, right? So it's not TE or TM. That's in region 1. Then in region 2, we have, what do we have? In region 2, we have EZ. Again, I'm just writing the Z component. Region 2 is K rho 2 square, Cn, Hn1 of K rho 2 rho, E to the I n phi, E to the I beta z. Similarly, Hz2 is K rho 2 square, Dn, Hn1 of K rho 2 rho, E to the I n phi, E to the I beta z. Okay, so these are just the Z components. Similarly, we get the phi components, E phi 1, H phi 1, E phi 2, and H phi 2, right? So we have the Z component, we have the phi component, and these are the components for which we need to apply boundary conditions, right? Because the continuity has to be satisfied for the tangential E and H across the boundary. And the tangential components are the Z component and the phi component, right? Based on what the boundary we have is. So I'm not going to write these equations out. They're kind of long, but you can look them up in the textbook, the Foundations of Applied Electromagnetism textbook. But basically, if you apply the boundary conditions, what do you end up with? Applying the boundary conditions gives us a few equations. So equating EZ1 with EZ2 and HZ1 with HZ2, we get the following equations, which is fairly easy to see from the above equations that we've written down. K rho 1 square, AN, JN, K rho 1, A. So rho is replaced with A because we have the boundary condition at rho equal to A. Maybe I should mention that. Let me go back up and say that. So this diameter here is A. Okay, radius, not diameter, sorry. Okay, so now that we know what that is, K rho 2 square Cn Hn1 K rho 2A. That's the first equation, I'll call it. And then we also have from the H field Bn Jn K rho 1A is equal to K rho 2 square Dn Hn1 K rho 2A. So this is the second equation. Okay, maybe I'll skip a page and then okay, so then we equate the phi components. E phi1 equal to E phi2 and H phi1 equal to H phi2 give the following equations. So these are somewhat long. Basically, you have n beta over A, Jn, K rho 1A, An plus I omega mu D, K rho 1, Jn prime, which is the derivative of the Bessel function, K rho 1A, Bn is equal to n beta over A, Hn1, K rho 2A, Cn plus I omega mu C, K rho 2, Hn1 prime, derivative of the Hankel function, K rho 2, A, Dn. That's equating the electric fields. And then equating the magnetic fields, we get I omega epsilon D, K rho 1, Jn prime, K rho 1A, An, minus n beta over A, Jn, K rho 1A, Bn is equal to I omega epsilon C, K rho 2, Hn1 prime of K rho 2A, Cn minus n beta over A, Hn1 of K rho 2 A Dn. Okay, so these are somewhat long, but algebraically they're long, but they're not really very complicated, right? Of course, in some sense, they are complicated because you have the Bessel functions and the Hankel functions and their derivatives, and that's what makes it complicated, but we'll see how to solve them. Okay, so we have four equations. If I just zoom out, you can kind of see them here, and we have four unknowns, which is the An, Bn, Cn, if I can find it. Okay, Cn, Dn. And really, all four are not unknown. We just need to know their ratios. So I need to know B in terms of A, C in terms of A, and D in terms of A. So you really only have three unknowns, right? Because the absolute values of these guys will depend on the amount of power in the given mode, but the ratios depend on the mode itself. right? So you have three unknowns basically. Let's say B over A, C over A, and D over A. And the fourth unknown is beta, right? We also don't know what beta is. So we really need to solve all of these unknowns. Another way to say that is that we don't know what K rho 1 and K rho 2 are. Right? So once we know K rho 1 and K rho 2, then we put it into the dispersion relation because we know KD, KC to get beta. Right? So really we have these four equations plus the dispersion relations to find three of the coefficients and K rho 1 and K rho 2. If you treat the two dispersion relations as two different ones, then basically you have about six equations and six unknowns, right? K rho 1, K rho 2, beta, then A, B, and C in terms of D. So those are the six unknowns. Okay, but it's really not that complicated to solve all of these equations, and that's what we'll see next. Okay, so let's actually do it rather than skipping the derivation. So I'll substitute equations 1 and 2 in 3, right? So basically I'm saying that I will, in place of C, I'll write this part. So I send all of this to the other side. And in place of D, I'll write it as a function of B. So that gives me C in terms of A and D in terms of B. I substitute that into these two equations where I have C and D. Right, so I substitute C and D here and here with the values up there, and that gives me two equations and two unknowns, which is AN and BN. And if you simplify that, you get this Bn equal to I and beta over omega 1 minus K rho 1 A square minus 1 over K rho 2 A square times mu D over K rho 1A Jn prime K rho 1A over Jn K rho 1A minus mu C over K rho 2A Hn1 prime K rho 2A over Hn1 of K rho 2A inverse times An. So that's one equation relating An and Bn. You can do the same thing with the other one. Maybe we can simplify this a bit further. So to reduce the amount of notation we need to carry around, we'll make some substitutions. So I'll say U equal to K rho 1A and IV equal to K rho 2A, which is the same thing as I knew A. Okay. And recall that, recall, which we looked at earlier as well. I can write the Hankel function in terms of the modified Bessel functions, right? And it has an imaginary argument, An nu R. Yeah, and this also, you can also show that Hn1 prime over Hn1 is equal to minus I Kn prime over Kn. So this is I nu A, and this is nu A. Okay. So with these relations, we can simplify that equation quite a bit. So you end up with Bn is equal to I n beta over omega times 1 over u square plus 1 over v square times mu d over u Jn prime u over Jn of u plus mu c over v Kn prime v over Kn of v inverse An. Okay. Similarly, if you substitute 1, 2 and 4, you end up with another relationship between Bn and An, which is Bn equal to I omega over n beta times 1 over u square plus 1 over v square inverse times epsilon d over u, jn prime u over jmu, plus epsilon c over v, kn prime v over knv times an. Okay, so I'll call these two equations equation 5 and 6. And now we're kind of in a position to solve them, right? So we can now eliminate an and bn because we have two equations. So essentially you just equate these two things or the two right-hand sides and then cancel an. And that gives you an equation that is purely in just terms of u and v, right? Which is called the transcendental equation. Transcendental equation. Right, so if you equate 5 and 6, you end up with this equation, omega square mu d over u, jn prime u over jnu plus mu c over v, kn prime v over knv times epsilon d over u, jn prime u over jnu plus epsilon c over v, kn prime v over knv is equal to n square beta square times 1 over u square plus 1 over v square. Okay, now recall that we also have another relationship, which was k rho 1 square equal to kd square minus beta square and nu square equal to beta square minus kc square. So this was from our dispersion relations, right? So from these two equations, we can equate the beta terms. You can show that basically just add them up on the left and right hand side. You'll end up with u square plus v square is equal to a square times kd square minus kc square. Okay, so now we have two equations and two unknowns, right? We have the transcendental equation, these two basically. So we solve for u comma v. Okay, so once we have u and v, then we can get beta. This equation or this equation doesn't matter, right? And once we have beta, u, and v, then we can go back and substitute into these equations to get the ratios bn over an from either of these, doesn't matter. Once you have bn over an, then you go back in here to 1 and 2, and then you can essentially find cn over an, which is directly given from these equations, and dn over an. Okay, so you have all the ratios. So maybe I should specify that. So, and then from this you can get basically beta, bn over an, cn over an, and dn over an. That's all you need, right? You don't know exactly what an the absolute values are because, as I said before, that depends on the amount of power in the mode, but it's the ratios that really matter, right? That tells you the modal distribution or the field distributions. Okay, so solving this transcendental equation is essentially the main picture that we need to kind of wrap our heads around, right? Like, how do you actually solve this? This is not a simple transcendental equation. It's pretty complicated, right? You have derivatives of Bessel functions, derivatives of modified Bessel function, and you also have ratios of quantities. Right? And the problem with that is that these guys we know have zeros, right? Zero Bessel function has many zeros. Modified Bessel function, this one doesn't have any zeros, but it blows up, or blows up at least v equal to 0, right? This one has zeros. So you essentially have quantities where you end up with maybe 0 over 0, or at least something finite over 0 on the left-hand side, right? And then again, you have a product in here. So it's like highly nonlinear. Right? So solving this even numerically is very difficult. Okay? But luckily for us, engineers have kind of figured out at least how to solve it to some extent. I think that's what we want to do today, is actually solve it and see how we get the different mode profiles of fiber optic cables. So the simplest solution is the TE/TM solution. Okay, so this is the simplest kind of case, TE/TM modes. Okay, so we go back here and we say, if I take this equation, so let me actually make a copy of this. Make a copy. Let's go down here and then paste it. Okay. So this part. Okay, so TA and TM modes are when n equal to 0. What is n? N is the azimuthal index, right? So essentially, how much variation or how many nulls and mode peaks there are as you go around in azimuth. That is what n is describing. And it's e to the I n phi. That's the index for the phi variation. When n is 0, it means that e to the I n phi is equal to just 1, which means there is no variation in phi. So now you're looking at modes that have azimuthal symmetry. Maybe it's like that, right? Or a mode that's like this. So it has to be azimuthal symmetry, azimuthally symmetric modes. Azimuthally invariant, I would call it, rather than symmetric. Okay, so under this condition, it becomes easy to solve the transcendental equation because the right-hand side goes to 0, right? So now you end up with two equations. This is equal to 0 or this is equal to 0. And we'll show that each one corresponds to either the TE or the TM mode. Okay? Okay, so what are the two equations? So you have basically this is equal to 0, which we'll put in red. And maybe I use a different color. So this is equal to 0 is one equation. And this is equal to 0 is the other equation. It's either or, right? One of them going to 0 is enough. Okay, but if I set this thing to 0, what does that mean? So if I go back and look at, let's actually rewrite that. Right, so n equal to 0 in this case, which means I have mu d over u, j0 prime of u over j0 of u plus mu c over v, a0 prime v over a0 v is equal to 0. Right, so if you go back now and we look at equation 5, that is equation 5, this one. Right, what we're saying is that this quantity is now equal to 0. Right, if this quantity is 0, I can basically take this term to the left-hand side, right, and then get rid of this inverse. And if this quantity becomes 0, it goes on the left-hand side, then that means an must be 0, right, or a0 must be 0. Another way to say that is that if you want this to be finite, and this goes to 0, then this also must go to 0, right? So essentially, it's the same as putting an equal to 0, or it enforces the condition that an must be 0 as well. But if we go back here and we look at EZ, right, EZ1 was an. Basically, an was the coefficient of EZ1. So essentially, if A0 must be 0, that means EZ goes to 0, which means what? Which means it's TE, right? So hopefully that kind of makes sense. Right, so this condition implies A0 equal to 0, which implies it's a TE mode. So these are all equivalent. Okay. So essentially, if you solve this transcendental equation for U and V along with the dispersion relation, which was this one, then you end up with modal solutions that must satisfy A0 equal to 0, which correspond to TE modes. Okay, similarly, if you use the other one, which is this guy, if you set this to 0, then so I would say similarly, if you solve the transcendental equation ED over U, J0 prime U over J0 U is equal to minus epsilon C over V, A0 prime V over K0 V. This gives TM modes. Okay, since this is the same thing as putting B, or this implies that B0 must be 0. Okay. Okay, so essentially you have these two kind of transcendental equations. We can simplify that a little bit more actually because of some of the properties of Bessel functions. So J0 prime U is actually equal to minus J1 U. And A0 prime V is equal to minus K1 V. So this comes from the fact that basically J0 prime, we had a equation for the derivative, right? Which we saw last time in the properties of Bessel functions. And we also have this kind of recurrence relation, right? And that essentially gives us, so you can substitute this term in here, and that gives you this relationship. That's obviously very trivial. Okay, so based on this kind of substitution for the derivatives of the Bessel function, we can put them in, and then that gives us mu d over u, j1u over j0u is equal to minus mu c over v, k1v over k0. This is for the TE case. And the other one was epsilon d over u, j1u over j0u is equal to minus epsilon c over v, k1v over k0v. So this gives TM modes. Of course, you need to solve this along with the dispersion relation for u and v. At u square plus v square equal to a square, ad square minus kc square. For u and v, and also for beta. Okay. So keep in mind that the TE and TM mode solutions for a fiber optic cable have no azimuthal variation. Okay, if they have no azimuthal variation, that is actually a nice intuitive picture as to what's going on. So these rays are called meridional rays. So if you look at kind of the ray picture, you can kind of treat them as, if I have my optical axis of the fiber optic cable, this is the optical axis, which is the axis of the fiber cable. These rays are rays that propagate crossing the optical axis in every bounce. So the cross section looks something like this. So these rays kind of bounce back and forth like that. So this is my optical axis. Okay, so meridional rays. So they're called meridional because they don't kind of go around the optical axis, right? They just go back and forth because they don't have any variation in phi. Okay, of course, you can make this kind of ray picture more rigorous by considering the angular spectrum and so on and so forth, but we're dealing in kind of the field distributions and the modes right now. We don't want to get into the angular spectrum here, but I just wanted to kind of give you an intuition as to what these rays represent. Okay. Now, one of the problems actually with having no azimuthal variation, okay, so I'll just mention that. So no azimuthal variation implies it has a null in the middle. Right? It has to be, because the mode is either going out that way, in which case the field has to be zero in the middle, or it has to be kind of going around in a circle. Again, in which case the field must be zero in the middle. Right? Because if you have a field distribution in the middle that's in some direction, then automatically you're breaking azimuthal variation. And that's one of the consequences of dealing in vector fields, is that if you have no azimuthal variation in the middle, you must be a null. That's a problem, right? Because we know that for an optical cable, you want to have power that's propagating near the core in the middle. Right? That's the fundamental mode in some sense. Right? So this kind of gives you an intuition that TE and TM are not the fundamental mode. Okay, why is that a problem? Because typically we care about modes, we care about the fundamental mode, right? We want to have a single mode propagating in a fiber, which is more often than not, pretty much all the time, the fundamental mode. If you have a single mode, it's typically the fundamental mode, right? And the reason behind that is that all other modes are in cutoff, so you have a bandwidth over which only this mode propagates, so it's very easy to excite it, right? And have only that mode propagate. So those fibers are called single mode fibers. We'll talk a little bit more about single mode fibers at the end, but this is a problem because now we have to actually solve the full transcendental equation in order for us to find this fundamental mode. Right? The simplified version of the transcendental equation where the right-hand side went to zero is not good enough. Okay, so essentially the fundamental mode implies the fundamental mode is not TE or TM. Mode is some combination of TE plus TM, which means it has EZ and HZ components and is a hybrid mode. So hybrid modes are modes that have both EZ and HZ components. So let's talk about that next. Okay, so now we want to discuss hybrid modes. Okay, so hybrid modes are modes which have both EZ and HZ components, and they're typically classified as EH or HE. Okay, so electric, magnetic, or magnetic electric modes. So EH means it's mostly TM. It's a mostly magnetic, which means that the magnetic Z component is much smaller than the electric Z component. And HE means it's mostly TE. Okay, which means EZ is much smaller than HZ. Okay, so it's almost like TE or almost like TM, but not exactly, because you still need them in order to satisfy the boundary conditions. Yeah, and to have also azimuthal variation. So we can maybe also look at the ray picture. What does the ray picture look like? So if I draw the cross section, so let's say that's the center, the ray kind of propagates like this. It's like bouncing off of the ends and doesn't actually intersect the axis. Okay, so these are called skew rays. So if you pick the cross section, it kind of looks, so if this is my optical axis, then it's kind of doing some kind of a corkscrew kind of pattern. Like that. Okay. Something like that. Okay. So this is the ray picture of what's going on. So it essentially gives us this azimuthal variation, right? Because this ray is kind of going around like that. Okay. So let's actually see how to solve it. So in order to go back, and if I, let's say, go back to this transcendental equation, and I want to see, okay, how do I actually solve this? And I said earlier that there's basically no hope of solving this even numerically because of how complicated these functions are. How do you actually expect to solve it analytically, right? So the way we solve it analytically is we make this big approximation called the weakly guided approximation. Or I should say weakly guiding approximation. Okay, so what is this approximation? So this kind of assumes when trying to solve the transcendental equation that ND is approximately equal to NC is approximately equal to some N, which is the dielectric, a common dielectric constant. Okay, so in other words, it's saying that basically the dielectric constant is almost equal, approximately equal, and mu D is exactly equal. So it's the same medium in terms of mu, and epsilon is also close enough that you can approximate it to be the same. Okay? Okay. So I should say caution. This is only to solve the transcendental equation. You can't start with this approximation from the beginning. Why is that? Right? So it's really kind of an unsettling approximation because what we are saying is that the core and cladding are made of the same material, right? And that is, in some sense, is meaningless, right? Because if the core and cladding are the same material, you have a homogeneous medium. And in a homogeneous medium, there is no such thing as a fiber optic mode, right? And that's why you have to be a bit careful in applying this approximation. So this approximation is only really true when you're trying to find beta. Okay? Kind of breaks down if you try to solve for the fields and everything using this approximation. Then it doesn't really work. Right? So that's why you have to be a little bit careful when using it. Okay, so under this approximation, under the weakly guided approximation, brackets, I guess, hybrid modes reduce to linearly polarized modes. Sometimes these are called the LP modes. Okay, so why is that? So when the refractive indices are the same, approximately the same, it's almost like a homogeneous medium. Right? Since it's almost like a homogeneous medium, what essentially propagating inside, the mode that's propagating looks very similar to a TEM or a plane wave, right? Like a locally plane wave mode. And that's why they're called linearly polarized modes. Okay. So let's actually see what that looks like. So under this weakly guiding approximation, the transcendental equation becomes omega square mu epsilon jn prime u over jnu ujnu plus kn prime v over v knv square equal to n square beta square 1 over u square plus 1 over v square. Okay. But also, since we have made this approximation that you're kind of in a homogeneous medium, beta is nothing but omega square root of mu epsilon, right? Because I have this mode that's now almost like a plane wave propagating in z, right? Kz, which means it doesn't really have any k rho component anymore. Since it doesn't have any k rho component, essentially beta is nothing but k, right? Which is why you can also make this approximation. Okay, so these two terms go away, and you end up with, let's erase this, erase this. So I'll put this in a bracket. This also comes from the weakly guiding approximation. Okay, so our transcendental equation now is just this. Right? So we can actually reduce this even further by using a few Bessel identities. So using some Bessel identities, you can show that Jn it reduces to, essentially you can just replace the primes with some of the other terms with plus minus coefficients. And you can reduce that equation to Jn plus or minus 1 u over u jnu is equal to minus plus kn plus or minus 1 v over v knb. Okay, where plus corresponds to EH modes, and we'll see why. And minus corresponds to HE modes. Okay, so you essentially reduce that big complicated transcendental equation into something simple. Okay, I want to re-index it just to make it a little bit simpler, right? So re-indexing from N to J. So I'm using a new index. We'll see what that does. So what I've done is I've kind of taken the inverse of these two. So I've taken inverse on both sides. And then I replaced N with, or N plus 1 with J. Not exactly, actually. Let me write it down and then I'll show you what I did. So re-indexing, I can write this as uj j minus 1 jj u is equal to minus v aj minus 1 v over ajv. Okay, where j equal to 1 is nothing but our TETM modes. Right? J equal to n plus 1 gives EH modes. Okay, and j equal to n minus 1 gives HE modes. And you can kind of see that. So this is what I was trying to say earlier, is that if I just replace j with n plus 1, this becomes n plus 1, this becomes n plus 1, n. And that's exactly the same thing as this when n plus 1 is, when you have n plus 1 case, right? I've taken the inverse, of course, to go from here to here. So, and the reason it is an EH mode is because if I set n equal to plus 1, then that reduces to the TM mode, right? And if I set n equal to 0, then this becomes j equal to minus 1. And HE we know corresponds to TE, right? So that's why we label them as EH and HE. But of course, you can also solve the differential equation, or you can solve this, find U and V, substitute it um, into the fields, and then see that you in fact get EH and HE modes. Okay. Okay, so this is the actual transcendental equation for a fiber optic cable under the weakly guiding approximation. And the reason I said that j equal to 1 corresponds to the TE and TM modes is because this equation is identical to what we solved directly when we did the TE TM case. Right? These guys, basically. Okay, of course, this is if you make these two equal and so on, then they cancel and then we get that equation. Right? Okay. So there are a lot of interesting things we can get from this. Like the first most interesting thing is the fact that TE and TM are degenerate modes. And the reason they're degenerate modes is that you have the same transcendental equation for both the TE and the TM case, right? Because basically epsilon's canceled and mu canceled out. You end up with this case where you have the same transcendental equation, which means the U's and V's turn out to be the same, which means the beta is the same. That's the meaning of a degenerate mode. So degenerate mode means they have the same beta. Okay. So these two are degenerate. Okay. Also note that EH n minus 1 is degenerate with HE n plus 1, right? Because maybe I should put a subscript n here and an n here, right? So HE, if I put n plus 1 here, so substitute n plus 1 in here, then that gives me j equal to n. In the EH case, if I put n minus 1 here, that also gives me j equal to n, right? So the j is the same. Basically, if I choose EH3, it's the same as HE5, right? EH3 and the HE5. So EH3 gives me j equal to 4. HE5 also gives me j equal to 4. And when they're both equal, the same j, which means they have the same dispersion relation, right? So there is a degeneracy between EHn minus 1 and HEn plus 1. These two cases also get the same beta. Okay? So what does it mean when you have so many degeneracies, right? So you're ending up with these solutions which are essentially like plane waves, which means that if I combine, essentially if I have plane wave, it's neither EH nor HE. And since it's kind of a homogeneous medium, we said that these LP modes are very similar to TEM or plane waves, something like plane waves. We'll see what they exactly look like, which means they should not have any Z component. Which means what? Which means if I add this and this, I end up with a case where the Z component becomes very small for both E and H, and I have very large radial components or azimuthal components. Right? That's the reason you end up with this degeneracy, because in this EH and HE basis, you don't have modes that have very low Z, very small Z components. You have to add them in the right way in order to get the modes that have very low Z component, very small Z component. And that's the reason that in this basis, the EH-HE basis, you have so many degenerate modes. Okay, hopefully that makes sense. So another way to say that is that LP modes are mostly TEM. EHHE modes are mostly TE/TM. And that's why you need to add them in the right combination in order to end up with these LP modes. Right? Because we know we should end up with something mostly TEM because it's kind of a homogeneous medium. Right? That's the big idea behind going to LP basis. Because in LP basis, you get unique modes. You don't have to deal with this kind of degeneracies. Okay? Okay. So combining degeneracies in EHHE basis to get LP modes. Okay, so how do you actually do this? So LP1M is the sum of TE. So here I only have one subscript because I'm only dealing with the azimuthal subscript. But of course, this has actually two subscripts, NP and NP, which then the P corresponds to the subscript, the variation along row. Right? We had the J and K row, right? And this K row has a P in there, right? Depending on the size of the fiber optic, the coherent cladding, and so on. Okay, so that's the second subscript which I'm bringing in explicitly now. So TE0M and TM0M, because you know these two are degenerate, and also HE2M and EH1M. Okay, so we haven't really established this degeneracy, the fact that these two are also degenerate with these, but that is indeed the case. Okay, so all of these modes have basically the same propagation constant, and that's why we lump them all into one LP. Okay, similarly, we have LP nu M is HE n plus 1M and EH n minus 1M. Okay, so going back here, we said that these two are degenerate. We showed that, in fact. I think we're lumping them into one mode, which is the LP nu M mode. Then we have another kind of LP mode, which is actually unique, which only maps to the HE1M mode. Okay, so here there is no degeneracy. So HE1M is good. It doesn't have any degeneracies, and that's why it's a special case. Okay. Now our fundamental mode is this LP, the special case mode. It's the LP01 mode, which is basically the same thing as the HE11 mode. Is the fundamental mode. Okay, that's important to remember. And it has no cutoff. So it propagates basically down to very low frequencies as well. So what does this mode actually look like? So that's my cladding. So that's my core, it's very small. This mode looks almost like a plane wave. The electric field, this I'm drawing is the electric field. It looks something like this. So it's almost like a plane wave that's propagating inside. And we know that it should be something like that because it is, in fact, almost homogeneous. Right? This is your HE11 mode. Okay? So that's the fundamental mode. So this is the fundamental mode. So if we actually write out all the modes, So let me just say modes of the fiber. So what are the different modes of the fiber? So the first one is what we just said, HE11, which is the same thing as LP01. And that has a mode profile that is somewhat uniform. And the field distribution is, electric field is something like that, right? The second mode is the LP11 mode, which is a combination of four modes in the EH and HE basis. So it's the TE01, TM01, HE21, and EH11. All of these have almost the same propagation constant, and they are usually lumped together with LP11. So LP11 looks something like this. So I should say this is kind of so it's kind of uniform like that, right? Maybe the core is somewhere here and the cladding is somewhere there, right? So it's not like this is the core. So the core is kind of in the middle there. Okay, and this mode has field distribution that's like this and like this. So it's kind of like you have to have a null in the middle because the field distribution changes direction. Okay, and that's the LP11. So, and it's not like a hard cutoff like this. If you actually look at the figure, it'll be like sort of maximum here, and then slowly decays as you go away. Okay, then the third mode is another single mode, which is the HE12 mode, which is equivalent to LP02. So what does this look like? This looks like kind of like this. So I have field distribution here. I have a null along row, and I have another maximum, right? So basically, yeah, you have a null and another maximum like that. Okay. And so on, right? So the second index basically tells you like how many nulls or how many maxima there are along row. And the first index tells you how many nulls or how many maxima there are in phi. Right? So for example, if you pick n equal to 1, or this second index is 1, there's one maximum, and then as you go out from the center. When it's 2, you have two maxima, one here, and then out. Right? Whereas if you pick first index is 0, as you're going around in phi, there is no maxima or null. Here, as you're going around in phi, there are basically two. The reason there are two is because it's a cosine function. So I'm just saying that there's one cosine along phi. Right? So you have one cosine has two maxima, I guess, right? One there and one there, or two nulls. And that's why you have one cosine going this way. So here there is zero cosines, right? It's kind of uniform. So basically, if you pick LP21, you can kind of see that it would be four quadrants like that, right? Because when you go around, you should see two cosines. So that's kind of the idea of this kind of naming basis. So you can kind of easily tell from just the numbers what kind of modal distribution it should have. So that's why the LP basis is really the more popular basis when dealing with fiber optic cables. It's the more natural basis. Okay, there are a couple more things I want to mention before we close. So one is called the V number. This is quantity, which is 2 pi over lambda a square root of nd square minus nc square. And that's nothing but a times kd square minus kc square, right? So this V number essentially dictates how many modes can propagate inside this waveguide, right? So basically, given a certain fiber optic cable, let's say you've given this A value, and the core and cladding refractive indices, you can calculate V number as a function of wavelength, right? And then you can see at what frequency different modes start to propagate, right? So V number for this mode is the cutoff for this mode, I should say, is at a V number of 2.405. And this corresponds to the first zero of the J0 function. Okay, so the first zero of the Bessel zero function it happens at this number, and that's what defines this V number quantity. Right, so at a wavelength where V reaches this, you end up with, beyond this frequency, basically, oh, sorry, I should say that this is not right. So there is no cutoff for the fundamental mode, right? So the V number of the first higher order mode is approximately 205. Okay, so given a certain fiber optic cable, you calculate the V number as a function of wavelength, and then you see that the wavelength at which the V number reaches 2.405 is the maximum or the smallest wavelength until which you have fundamental mode propagation. Right? Once you're at a wavelength where V reaches 2.405, the second mode or the first higher order mode, which is LP11, will start propagating, and then you don't have a single mode fiber anymore. Okay. So V number for this mode, the second higher order mode, is 3. Okay, no, it's wrong. Oh, I had shapes clicked. It's 3.83. Okay, so this is the first zero of the J1 function. Okay, so the wavelengths for which V is less than, say V less than 2.405 implies it's a single mode fiber, which means only one mode propagates, right? Now, another kind of useful thing with the V number is that when V number is large, for large V number, only for large V numbers you can use this. You can show that the number of modes is approximately equal to 4V over pi square. Okay, so you can kind of show this by calculating the density of modes of a given fiber optic cable, and this calculation is available in some books. But basically, when the V number is very large, so let's say you're using a multimodal fiber. So in a multimodal fiber, if you want to calculate, okay, how many modes are actually propagating in this fiber at a given frequency, at that frequency and the given fiber, you calculate the V number, put it into this equation, and that gives you a good approximation to the number of modes that are propagating in the fiber. Obviously, this is only valid when V is very large. Okay. Okay. So although we said that these are single mode fibers, in reality, every fiber has two modes, right? If it has this mode, two degenerate modes, then it also has this mode, right? Just from the symmetry in phi, right? And these two modes are also degenerate, although they're orthogonal. And therefore, you also need to kind of make sure that when you're propagating in a single mode fiber, if you want to maintain polarization, so there is something called polarization maintaining fiber. EM fiber. Right, so these fibers not only have a single mode, they can also maintain the same polarization. Now, if you pick a general fiber like this, like a single mode fiber, like that. Now, if I twist this fiber, let's say it's twisted this way, right? Someone twists it in phi, then the mode has no idea that the fiber has been twisted, right? So it propagates as if nothing happened, which means now a mode that was oriented this direction with respect to the fiber's coordinate system gets rotated into this direction with respect to the local coordinate system of the fiber. Right? So essentially the polarization is not maintained, and that's not a good thing depending on what you're trying to do. So in some cases you want to maintain the polarization, and in that case you have to use a polarization maintaining fiber. Okay, so what they do there sometimes is that, this is just an example. So you have your core and cladding, and then they add some kind of doping or extra material here and here, and in different shapes for different kinds of fibers, so that there is some stress that is induced in some direction, right? So that basically changes the beta of the mode that's propagating the dispolarization versus this polarization. And because the beta is different for this mode and this mode, you cannot go from one mode to the other mode because you need phase matching to occur in order for modes to mix, right? So that's how they kind of maintain polarization as the mode propagates through the fiber. Okay. So essentially, we discussed single mode fibers and what the main mode is, which is the HE11 mode, and this is the most popular mode when you want to do data communication, because you don't want different modes to propagate, because different modes propagate with different betas and different wavelengths, and it introduces severe dispersion, right? Also, if you want to maintain a Gaussian profile for your modal distribution, you need to make sure that it's a single mode fiber. And multi-mode fibers are useful when you just want to propagate power over long ranges. You don't care about phase or polarization or modal distribution. You just want to have a lot of power going through the fiber. It's much easier to use them because it's much easier to launch waves into them, and they have a very large core and so on and so forth, right? Whereas polarization maintaining fibers are even more restrictive than single mode fibers. So they're single mode and they maintain the polarization. And this can be very useful if you want to use a polarization filter or a polarization based phase shifter and so on, right? If you want to maintain the polarization. Okay, so that's pretty much everything I wanted to say about optical fibers. We spent quite a bit of time in developing theory behind the fiber itself. We derived from first principles what is the transcendental equation that you need to solve for to find the different modes. And we said that in the simple case of no azimuthal variation, you end up with TE and TM modes. But that's not very useful because they're not the fundamental mode. So we wanted to solve for the fundamental mode, and to do that, we use this weakly guiding approximation, which is you have to be a bit careful in using it, what it really means. And we showed that under that approximation, you end up with a fairly simple transcendental equation. And from that, we saw that, even without solving it, you can see that there are many degeneracies. And the degeneracies exist because under the weakly guiding approximation, a better basis which represents these almost TEM modes is the LP basis rather than the HE and EH basis, which were more suitable for TE/TM modes. So we saw what this LP basis is, what the first few modes are in the LP basis, and what they represent, what they look like in the EH and HE basis. And then we saw what the modal field distribution looked like for the LP modes. And we also did a brief discussion of single mode, multi-mode, and polarization maintaining fibers. Okay, so hopefully that was useful and enjoyable. And if you have any questions, you can leave them in the comments. If not, I'll see you in the next video where we'll start discussing spherical wave functions. Thank you.